So before I get into the distribution power flow analysis, I just want to do a little bit of review on the power flow I guess we would associate with transmission analysis. And this would be something you would see if you'd taken like a undergraduate class in power system analysis. At NC State, this class would be ECE 451. In the methods we talk about in a class like that would be Gauss-Seidel and Newton-Raphson. I'm just going to talk about the Gauss-Seidel method. And so this shows a simple 4-bus circuit. You can see we have it looped. And we have a slack bus in this case, where this is sometimes referred to as an infinite bus. And what we want to do is we want to calculate the voltages at the unknown locations at buses 2, 3, and 4. Now, the definition of a slack bus is we know the voltage at bus number 1, so we don't have to calculate, that's going to be a known. Another sort of bus type we could have would be to have what's called a PV bus, where you have real power injection voltage specified, but we won't consider that in this particular case. But this is a non-radial system. This is a loop system, which is typical transmission. And we have various line impedances, which are denoted by having a bar over the Z. So what this means is this is a series resistance and reactance for the line. Now, recall that one thing you can do if you have a power system is you can create what's called a bus admittance matrix. And the terms are such that the off-diagonal terms of the bus admittance matrix, which is denoted by capital Y, are going to be minus 1 over the impedance between the two nodes. And then if I have a diagonal term, this is going to be the summation of the inverse of all line impedances that are connected up to that particular node. So for example, if we're talking about node number 1, if I want the Y11 term, I've got 2 lines connected to it. I take 1 over its line impedance plus 1 over its line impedance, and that gives me the diagonal entry. So anyway, this is what we refer to as Y-bus building. One nice feature of having Y-bus is it gives us a way we can formulate a power flow. And so I don't have to worry about bus number 1, but if I want to calculate a voltage at bus number 2, I know that the injected current in bus number 2 is going to be Y21 times V1 plus Y22 times V2 plus Y23 times V3 plus Y24 times V4. These are the matrix entries in the bus admittance matrix that link current injected into node 2 with the voltages at all the different buses in the circuit. And so what I would do in order to set up a power flow is I then make use of the fact that the current injected at bus number 2 is a complex conjugate of power divided by the complex conjugate of the voltage. So that's P minus JQ at bus 2 divided by V2 conjugated. And what I could do is I could take this equation and I could use this to solve for V2. And what this does is it gives me this first equation here. I could do something similarly for buses 3 and buses 4. I get this second equation, I get this third equation. And basically this is a simple set of power flow equations, which basically can be used to calculate the various bus voltages for buses 2, 3, and 4. Remember, I don't need the voltage for bus 1 because that's fixed. So if I want to go ahead and use these formulas, this is what's referred to as a Gauss-Seidel technique. Given that the voltage at the slack bus is fixed, and I want to find the other 3 voltages, I make some sort of initial assumption for what those voltages are. And that's denoted with a superscript of 0. That means that's the initial guess. And usually these correspond to nominal or rated voltage. That's usually the starting point. 1 per unit if we were doing this in per unit. And so what I use these formulas for is if I start off with an initial guess for these other voltages, then I start by getting an update for the voltage at bus 2, which is denoted with the superscript of 1. And so this is all going to be based on knowing the initial guess of the various buses, and I could use this to provide an update for bus number 2. Now, once I have that update for bus number 2, then what I do is I go through and do the same set of calculations for bus 3, but this time what I use is I use the update from the previous step. So I get an update for bus number 3, and then I use this update for bus 2 and 3 in order to get an update for the voltage at bus 4. And what I can do is I can go through this same set of steps over and over and over again iteratively until those voltages converge. And so that would be a type of a power flow technique, which we'd use in a class like 451, which is more for grid connected power systems. For distribution, we could use this technique. However, it turns out that for distribution, a lot of these Y terms in here would simply be 0 because the distribution circuits are rather sparsely connected. Usually one bus is just connected up to maybe 2 or 3 other buses. We don't need to have this really complex admittance matrix to describe a distribution circuit because so many of the terms in the admittance matrix would just simply be 0. We could do it, but it's not that efficient. And so we usually come up with more targeted techniques for distribution circuits. Okay, so if you're coming up with a good distribution power flow, what you would want to do is you would want to take advantage of the radial or non-loop characteristics of the circuit. That'd be one thing you want to do. You would want to have some type of algorithm that you can model not only 3-phase, but 2-phase and single-phase elements. So it's hard to base this just on symmetrical components. The line models would have to be able to handle unbalanced 3x3 line elements or 2x2, let's say. So we got to have this ability of handling unbalanced self and mutual impedance terms. The loads could be imbalanced as well, have different loading on phases A, B, and C. We have to do things like model not only substation voltage regulation, but we have to model line voltage regulators as well. And so that's something that's a little bit different than from what we have in transmission. And then we have to have a methodology for coming up with our load model. Like I said before, we need to have a load allocation type of method that works in conjunction with the power flow. So all these different sort of things are things we would have to have in a distribution power flow, which we wouldn't necessarily see for transmission power flows. So to show you how this would work, let's just look at one line element, and let's assume this is single phase for now. This is going to be single phase for now. We'll extend this to 3-phase later. And let's suppose I have a fixed voltage on the left, which represents the regulated substation voltage, the top of the feeder, have just a single line element, and I've got a load, constant power load, 1 MVA, 0.85 power factor. And what I want to do is I want to find this particular voltage. What makes this difficult is that current flow is related to power and voltage, where current's going to be S conjugate divided by B conjugate, which is a nonlinear relationship. Okay, this is a nonlinear problem we're trying to solve, which there's no closed form solution for in one iteration. So I've been having you guys up to this point start from the load and work back toward the source because that would make it linear. But in general, when you're doing circuit analysis and you're using a power flow, you're going to work in the opposite direction, right? Because you have a computer algorithm that can let you do iterations and handle the nonlinearities. So the way this is going to work is similar to the Gauss-Seidel in a way, is I make an assumption of initial set of voltages in my circuit. And so I'm going to usually assume the load voltage is it rated initially. That's going to be with the 0 and the superscript, right? Then what I'm going to do is I'm going to use that initial guess of my voltage to calculate the load current. And then based on the load current, what I'm going to do is I'm going to work back up toward the source and sum all these currents up. And then what I'm going to do is work back in the opposite direction and get an update in the voltage. All right. So I probably could add in here, not only do I want to calculate the load current injection, but I also want to calculate the line current. And then once I have that line current, what I'm going to do is I'm going to update the load voltage. And then I'm going to check a convergence criteria. And if I haven't converged, what I'm going to do is I'm going to go back up to step number 2, and I'm going to repeat the process over and over and over again. And this technique that will extend pretty soon to multi-segment circuits, I generally refer to it as a sweep technique. Sometimes people might refer to this as a ladder technique. And this works in circuits where you don't have loops. So you have a very clear-cut path going from the load all the way up to the top of the circuit and then back down toward the loads again. So if we're going to apply this approach on this very simple circuit here, then we would start off by assuming that that load voltage at the initial iteration at 0 would be rated, be 7,200 volts. That's 12.47 divided by square root of 3. We can just go ahead and start off assuming this is at 0 degrees. And then what I would do is I would calculate the load current. And the load current is going to be S conjugate divided by V conjugate. So I've got 1 MVA divided by 7,200. I've got the complex conjugate of the power factor angle, so it's minus 31.8 degrees. This gives me a load current of 138.9, which is also equal to the line current for iteration 1. All right. So once I've got this, and what I could do is I can start from the top of the feeder and work back toward the load. And so the load voltage is going to be the source voltage minus the line impedance times this current flowing through the line, which turns out to be the same as the load current in this case. So the 7,200 minus 1 plus J3 times this initial value of line current is going to give me an update for the load voltage of 6,868.2 at an angle minus 2.35 degrees. Okay, so you can see here I'm starting to get a voltage drop, which what I expect to see. And so this is the result we would get at the end of iteration 1. Now this set of steps, assuming a nominal voltage at the load, calculating a line current based on that nominal voltage, and then calculating a voltage drop, 7,200 minus the 6,868.2. This is the same voltage drop we would get if we use K factors. And so you can think about a K factor as like a first iteration of a power flowing away. And then what we're going to do is we're going to add more and more iterations. We're going to get more accuracy. All right. So K factors are sort of like doing the first iteration of a power flow, and which is useful if we just want to get a good approximation. So now, once I've got this value updated for the load, then what I would do then is I would do another iteration on this, because I know I haven't converged to a voltage yet. You know, I went from 7,200 to 6,868. That's a pretty large change, right? So then what I would do is I would go through and I would update this current. I'd update this load current, which, by the way, is the same as the line current. Okay, it's the same as the line current. And now I get a line current of 145.6, and I go through and I do this voltage drop calculation again. 7,200 volts at the source, take the drop across that line element, and now this is 6,840.3 at an angle minus 2.35 degrees. Now, what I'm going to do next is I'm going to compare this value I just got to the value from the previous iteration. And so if I were going to look at that as terms of a percent change with respect to the nominal voltage, then that gives me a percent change of 0.39%. Well, is this good enough? Well, it kind of depends how much accuracy you need in your solution. You'll see in a program like Windmill, you can actually set this percentage. And normally I would probably set it where I'm getting within 0.1%, something like that, right? That would probably be good enough. That's probably within the accuracy of your data, right? And it doesn't take a lot of iterations in order to get that type of convergence. And so you would compare this to a convergence criteria, maybe 0.1% or 0.01%, whatever. And if it hasn't converged yet, then you would keep doing more and more iterations, and you successfully be improving on this result. So let's suppose this isn't good enough. Let's suppose I want to get below 0.1%. I'll do this one more time. I'll go through and I'll update the load current. Keep in mind, this is the same as the line current. And then at the load, the next update is going to be the source voltage minus the drop across the line, which is 6,838.8. This time, if you compare this voltage to the previous iteration, you could see this error is 0.02%, which is, if I have my criteria is 0.1%, that means I'm done, and I can go ahead and start printing the results out or doing something with the results. One thing I might want to do is calculate line loss. And so line loss is going to be the current squared for the line times the resistance of the line. If I do this calculation, this gives me 21,374 watts. And so I can get other things from this as well. I can get real and reactive power flow on the line. But basically, this shows kind of how our power flow works for just like a one line segment. Now, one thing you have to watch out for when you're doing this is what would be the impact of having three-phase modeling if I had unbalanced feeders. And this is I kind of showed you before when I was running Windmill in the last online segment. But if I had, like, say, a 22.86 kV circuit, and let's suppose I look at this construction that's 477 ACSR, I've got a 4-watt neutral. It turns out what I'm going to get in this particular case is I'm going to get a 3x3 matrix, which has these values here in ohms per mile. Note that these terms have off-diagonal entries which differ. All right, so you're going to get a difference between ZAB and ZAC because the spacing's not the same for all the different combinations. If you have a overhead that looks something like this, the spacing between A and B is different than the spacing between A and C. And so if we don't transpose, then I'm going to get unequal off-diagonal types of terms. And so if we were going to then do the same type of analysis, but instead do this for three-phase, how would this differ then? Well, what I would need to do in this case is these currents, instead of being complex numbers, they would be a 3x1 vector where I'd have terms for A, B, and C. They still be complex numbers, but I'm going to have a 3x1 vector in this case. When I'm doing this calculation right here for the voltage drop, source voltage would be a 3x1 vector. I'd have to subtract off a 3x3 times a 3x1, which is going to give me 3x1, which is now going to give me values for load voltage for phases A, B, and C. So this gets kind of tedious to do by hand, and this is where you would switch over to a program like MATLAB for doing something like this. So what you could do in MATLAB is, since it supports matrix operations, is you would have ZABC. This is how you would put this into a 3x3. You would have a line length, so you can modify the net Z by the line length. You would have your line voltage, you'd have your line to neutral value, you'd have your power factor, and then what you would do is you would initialize your voltages. And here, this is the voltage at iteration 0. And so you'd have your A phase, you'd have your B phase, and you'd have your C phase values. And note what I'm doing here for the B phase is I'm making this at minus 120 degrees, and for the C phase, I'm making this at plus 120 degrees. Then when I do my iterations, actually they're pretty straightforward in matrix notation. So I've got I naught in this case. I think when I was doing this in the notes, I was actually calling this I1. It's not a really big deal, but basically what I'm doing here is I'm calculating my initial current. This is going to be 3/1. And then when I get V1, then what V1 is going to be, it's going to be the substation value minus the dropper across that line. And so this actually was the original values across the load, but also going to be the same as the substation value. So I can get an update for V1 in this case. And once I have this update V1, then I can run this back through again and I get an update which gives me V2. And basically what I've got here is I've got a couple different iterations. I could do a check here to see if I've converged. I could use look at the tolerances. If the tolerances aren't good enough, I can do some initial iterations on here. And I could maybe just put this into a loop to speed this up. But what I'm going to get in this case, when I use the matrix approach for the voltage drops, is I'm going to get values for VA, VB, and VC. And what you see is that these voltages do not have the same magnitude. So even if I have what would look like to be a balanced load with the same powers for phases A, B, and C, as long as I have a non-transposed line where the off-diagonal terms in the Z matrix for that line are not the same, I'm going to get a slight difference in the voltages. All right, I'm going to have one voltage is going to be high, I'm going to have another voltage is going to be low. And what we're really more concerned with is the voltage is too low. Now, if I did this using the assumptions that things are balanced, let's suppose I converted this into sequence calculations, I just did a per phase equivalent, then the way I would do this is I would just simply take the average of the diagonal terms, I would take the average of the off-diagonal terms, and if I had that value ZS minus ZM, that would give me a positive sequence impedance. Because this is doing per phase analysis. This would be like running a balanced power flow. And then Z positive sequence would be ZS minus ZM. If I multiply this by 5, then this would give you this value here for Z1 that I would use in my calculations. And so now if I go through this set of steps again, this probably should have been I1 and I2 to correspond to my other notes. But anyway, I can go through and I could do the same set of calculations again. This is balanced analysis, assuming everything's transposed. Now I get a voltage of, as shown here, 12,701. So how does this basically compare? Well, basically, it's kind of somewhere in the middle in a way, right? It's not the low value, it's not the high value, it's somewhere in the middle, but it doesn't really properly give me the lowest value. It's actually off by about 63 volts. That's not really a huge value. I mean, we're still kind of in the ballpark here. But you can see that if I use the per phase analysis, it doesn't really give me the absolute lowest value of voltage. And so this could be important later on if I had a lot of imbalance in the circuit, this is going to add up and would give me some differences in what I would see in doing the balanced circuit analysis. Anyway, so anyway, what these power flow programs are going to be doing is they're actually going to be working more like this, is they're going to be doing these calculations with these 3x3 line impedances or 2x2 or 1x1 line impedances. A lot of this grungy detail is kind of hidden within the program. It becomes kind of hard for you guys to work this way unless you're going to be writing code now, which is a little bit more than what I need you guys to do right now. But just realize that what programs like Windmill are doing is they're actually working directly with these 3x3 terms. And what they're actually doing is they're doing matrix operations instead of just operations on regular complex numbers. All right, it's all in terms of matrices. Okay, so let me go ahead and I'll stop here for this segment, and then when we come back, we'll look at the multi-segment case.